Okay,
Do you
everybody,
see
tonight's speaker is Raipudaman Malhotra. He earned his PhD at the University of Southern California and spent his career at SRI International, specializing on energy-related issues. He published over 100 peer-reviewed articles and several technical monographs. In 2010, he co-authored A Cubic Mile of Oil, Realities and Options for Averting the Looming Global Energy Crisis. The book is a citizen's guide on energy and to call for an informed public debate on energy, arguably the biggest challenge we face. In 2005, he was named an SRI Fellow. In 2015, he received the Storch Award from the American Chemical Society's Division of Energy and Fuels. In 2018, he was named a Fellow of the American Chemical Society. In 2019, he was inducted into SRI's Hall of Fame. Raipudaman.
Thank you, Bruce. I'm going to share my screen. Are you seeing it?
I am.
Okay, good. All right, so we have talked about in this forum before, about the cubic mile of oil, the book, the scale of the energy challenge, and then how we are going to get to zero emissions. And you all know my spiel, basically, that we have to really expand the use of nuclear energy. And in that, I basically mean the only one that we have is the fission. Fusion, there's a big hoopla going on this week with the National Ignition Facility achieving net positive. But that was a net positive of the laser energy that was shot into the pellet and what the pellet released. But it's a very important milestone. Up till now, it had all been negative. But anyhow, that's a technology still decades away from any commercialization. But right now, we really need to get on with our fission technology that we have, and that does provide us with clean, safe energy in copious quantities. And if we just expand it, we could be much rather. But that alone also will not be sufficient. There are a few other things that need to be done, and I'll be touching on those. So these are the ancillary technologies or enabling energy technologies. And two of them that I'll talk about today are hydrogen and carbon capture. Why isn't it advancing? Okay. So we'll begin with a quick recap of the global energy status, look at the current sources and what is needed, and then I will talk about these emerging technologies that are coming up, which is the hydrogen and carbon capture. Ammonia, I don't think I will spend much time on. And we'll look at the advantages and the limitations of each of those and try to sift through the hype. So this is the graph courtesy of the BP, where they showed the primary energy consumption. This is the global in exajoules, and from different sources. Do you see my arrow over here, the pointer, when I show this?
Yes.
Yes? Okay. So this top band is the oil, followed by natural gas, followed by coal. These three are the ones that are really dominating. And then we have nuclear, hydro, and renewables, which is both which is largely wind and solar, and some geothermal and biomass, but the biofuels. There is also the non-commercial biomass, which BP does not include. I try to include in my cubic mile oil discussion, so that's why the numbers don't always jibe. But anyhow, this is all in exajoules. Roughly, this is about the top mark over here last year, is about so 400 exajoules is about 4 cubic miles. It's actually more than that. It should be, there's a little, anyhow. So I have about 4.2 CMOs is what my estimate is at the moment. So 100 exajoules to a CMO is roughly okay. As a first approximation, I think we can just take with that and move that. But the point that I'm really worth noting is that the technologies that we are so far following are really very, very small, and there is still a lot of work to do, a large amount of things and to be replaced to get the carbon to zero. And we do need, there is no way that just by downsizing or by energy efficiency, there's no way that we could eliminate it, or the carbon emissions just by that. And let's look at the sectors, consumption sectors, where emissions occur. So transportation is a big one. About 23% of the emissions are from transportation. Well, in transportation, whereas the automobiles are concerned, yeah, we can electrify them and maybe produce electricity cleanly. That's one way of doing it. But there are sectors like airplane shipping, air travel, long-range shipments, and shipping is really done with diesel at the moment, or marine oils, and electrification is just not feasible on those at the moment. There's another thing, which is the industry. Industry uses it for lots of reasons, like producing fertilizers, which goes into the food. So that's part of the agriculture also, but industry subsumes that. All the plowing and the combines that they work with, that's also in agriculture, but that's also part of the consumption that happens. Then there are products that industry produces, like fertilizer, methanol, ammonia, or a whole bunch of plastics. Plastics are, they comprise only about 4 or 5% of the oil that we use. The rest of it goes into making other things or metallurgical purposes. Industry, the big one is for emissions is the concrete, and then also steel and iron. So those, and aluminum, these are the ones that really have copious amounts of emissions. That's where that building materials comes in, fair amount. And then building operations are the services that we use for lighting, heating, ventilation, information, communications, entertainment, all that. All that is pretty much electrical. So those things could be, but the heating of the buildings right now is done largely with natural gas. Natural gas is also used a lot in industrial heating. And those things could be electrified, perhaps. But sometimes it is not easily doable because of the temperatures and things that are, or the locations where it's needed. So how do we eliminate carbon emissions in those cases? And that's where the people are thinking about, of saying either we use hydrogen as a fuel. You could use that instead of methane. You get very high temperatures, and you could, there are many processes. You could do smelting operations using hydrogen. It's called DRI, or direct reduction of iron. That's a feasible, that's already established technology. It hasn't been expanded. It's not the one that is used most of the time, but it could be. It's a little more expensive, but that's the little price that you have to pay to do this. And the other one is to go with carbon capture. So, well, let's the emissions happen, but then let's capture the CO2 from the air and try to do something about it. As such, I think we will need to draw down the carbon that's already in the air, because we have reached way beyond, let's say, I think I have a slide about it. No, this is getting to the hydrogen part already. Okay. We already have, about 420 some ppm of CO2 in the atmosphere, and we want to be around 350. Anyhow, so now that we are on this slide was just to show you about, well, hydrogen has been making a lot of news. It's a $1 trillion thing. Green hydrogen gets a boost. Hydrogen, the fuel of the future. Lots and lots of headlines. And the things like, this is the fuel of the future is what I was taken by. And I said, well, hydrogen is an interesting thing, because when you burn it, it doesn't produce any carbon dioxide. So it's a very clean fuel, but it doesn't occur. It may be the most prevalent element in the universe, but it's not there. It has some good attributes. It's a storable form of energy, unlike electricity. You can put it in a tank. Combustion with oxygen releases more energy per unit mass than any fuel, better than diesel, natural gas, or any of those. And it produces only water. It can be used in internal combustion engines. Modify your car engine to burn hydrogen, that's possible. Or you could use it in a fuel cell, produce electricity, and have a fuel cell electric vehicle. Then it could also be blended, and so far they have demonstrated that you could blend it up to 30% with natural gas, and then you can distribute it in existing pipelines, and you can use it for industrial heating as well as for power generation. So power generation turbines could be, you can cut back the hydrogen, so you can reduce the carbon footprint of the electricity that you are producing by using hydrogen. It doesn't eliminate it completely, but it can cut back. And right now, direct combustion of hydrogen is really not used in many places. Perhaps some as a fuel directly. It's in those hydrogen torches. There are some, and the only one in a large amount is the rocket fuel. It's particularly good because it has the highest specific impulse. That's a parameter that's particularly of value in the rocketry industry, and so that's the reason that some of these big rockets use hydrogen as a fuel. So they have hydrogen and oxygen being burned together in the thrusters. Let's look at the limitations on this side. As I said, yes, while abundant on the Earth, it's present in compounds, such as water. So it's in combination with oxygen, or it's a compound with the carbon, as in various hydrocarbons, or in biomass as carbohydrates or proteins or what have you. But these are all, hydrogen is not H2, it's HCO or whatever, any kind of molecule that's made up with that. Producing elemental hydrogen from these sources will require input of energy. And so if you start with water, for example, yes, you could put in energy and get hydrogen, and then when you burn hydrogen, you get back water. So first law of thermodynamics, for thermodynamics will tell you that well, you're not going to get any more energy than what you are going to first put in. You will be short of it. So it's a sink. It's not a new energy source, but because it has some value, you may want to consider using it under some conditions. Also, as an energy density, I mentioned earlier in the slide that it has the highest energy density per weight, but per volume, it's miserable. So this little chart here will show you that. I've looked at just three fuels here: hydrogen, natural gas, and diesel. We're looking at megajoules per kilogram of the fuel. Hydrogen is 120. Natural gas and diesel are about in the 40s, high 40s or low 40s. But if I look at the megajoules per liter, now for diesel, it's say 4.8 megajoules per liter. But natural gas, well, I have to produce liquefied natural gas, which is I have to cool it down to minus 162 degrees. It's 2.6. And hydrogen, which I have to go down to minus 253 degrees C. So there's an energy penalty for cooling and keeping it there. It's only 1.15 megajoules per liter. So it has very, if I look at it, a gallon of gasoline has more hydrogen in it than liquid hydrogen. That's really mind-boggling when you first realize it, that a flask of minus 253 degrees C, full of liquid hydrogen, there is less hydrogen in that than when it is combined with carbon and makes gasoline. And of course, this doesn't take into account the energy cost of cooling and compressing or any of those things. So there are challenges to it. So let's look at hydrogen, where it is, what's the current status of this gas at the moment. It is widely used industrial gas. It's used in petroleum, petrochemical, and fertilizer industries quite a bit. About 90 million metric tons, which is about 11 exajoules or 3% of the global energy. That's the scale at which the world is currently using hydrogen. There are three main methods of producing it. One is electrolysis, which is talked about, which is rarely used. Only about 5% of the hydrogen is produced that way, which is hydrogen plus electricity going to oxygen and hydrogen. And it takes about 50 megawatt hours of electricity to produce 1 ton of hydrogen. The other one that is used mostly is the steam methane reforming, which is starting with natural gas and making a chemical reaction with steam. That's why it's steam methane reforming, and this is the equation. But in this, you can see that every time you produce some hydrogen, for each gram of hydrogen, you will be producing 5.5 grams of CO2. So there is a CO2, if you want to get away from CO2, this is not a desirable way of producing hydrogen. The other one, which is used for the almost equal amount, 45% of it, is called coke or coal gasification. These are now in the petroleum industry or coal industry, the final residues that are there. It's basically carbon, steam. You get a carbon monoxide of hydrogen, and then you do what they call the water gas shift reaction. Anyhow, the net result is that you can get carbon plus 2 hydrogens giving you CO2 plus 2 H2. In this case, you get 11 grams of CO2 for every gram of hydrogen that you produce. There are about 200 projects in about 22 countries around the world with a lot of investment looking at what they call this electrolysis or some kind of clean hydrogen productions. So either they are going to take this but trap the CO2 away. I think, let me show you, go to the next slide.
Can I ask a question now, or would you rather we waited till the end?
Of course, please stop me. Yeah.
Okay, so on the last one, your 50 megawatt hours, do you know what fraction of the energy in that ton of hydrogen is? I mean, is that like, 10% of the energy you get back out of it? I mean, there's some things where you put almost as much energy into producing it.
Yes, it is a fair amount of it. So you see, so per kilogram. So I changed the scale over here. I should do that. I should have kept the units a little consistent. Okay. That's a little, but I have over here. So hydrogen, it's a fair amount. I mean, this 120 will be the 120, and 50 megawatt hours. should be able to do it.
Don't want to put you on the spot. That's okay. We can come back to it later.
It's not, it's pretty bad.
Yeah,
I mean,
okay.
it's not positive. I mean, that's the net reaction. That's just the thermodynamics right over there. Now, I will tell you about that the 50 megawatt hours is about 50% efficient.
Okay,
Or
that's what I want
70%.
to know. 50%. Yeah, that's a
50
big
to
penalty.
70%. We'll talk about that in a minute. In another minute, I'll be talking
Okay.
about the energy efficiency of those processes. So it's coming. So you'll hear quite a bit about green hydrogen, pink, purple, all kinds of colors of hydrogen. And this is the green hydrogen is the one that everybody talks about, but that's not the one that they are producing. They're producing mostly gray, brown, and black here, hydrogen. So there's a mismatch. And people are trying to say, well, we'll take this thing, but we will capture the CO2 and they'll make it better. Okay, we'll see when that happens. So depending on what is the production technology, whether it's produced by electricity or whether it's produced by fossil fuels, they have ascribed hydrogen with different colors. I wish they had just gone with the simple metric of so many tons of carbon per ton of hydrogen. That would have been perhaps a better way of doing it. Anyhow, so they label it green if wind and solar power is used for the source of electricity. If nuclear power is used, it's called pink hydrogen. If it's just the mixed power grid, that depends on where you are, because in Oregon, of course, we have a very good, very green power. It has got very low, relatively speaking, carbon intensity. Because we are blessed with a lot of hydro right around the corner here, and also wind. But many other places, it's much higher. So that's if it is electrolysis for the mixed grid, a mixed origin of grid power, it's a medium greenhouse gas emissions with that. It's minimal with either nuclear or with wind and solar. And those are those colors. But let's look at what they do with, if you use natural gas or coal, and then you combine it with carbon capture, which we'll talk a little later, then you could, in principle, have very low greenhouse gas emissions associated with that hydrogen. And so that's referred to as blue hydrogen. There's another one, which is the turquoise, which is you start with these hydrocarbons, but don't convert it, but you just really heat it, pyrolyze it completely. So your products are solid carbon and hydrogen. It's not practiced industrially at the moment in any case, but this is in any significant amount, but it's demonstrated, it's talked about quite a bit. But the question is, well, it's a solid carbon and it's not in the atmosphere then. All right, so that's in terms of the hydrogen production. I didn't want to go too far into it, but you will hear green hydrogen. I wanted to make sure what green hydrogen is. That's only when greenhouse gas emissions are very low. People don't talk much about the pink hydrogen, but I think this nuclear powered hydrogen has a much better chance of saving us. Here's a cost thing. This hydrogen that we produce from natural gas with steam methane reforming is about $1 a kilo, $1,000 a ton. And currently, the green hydrogen costs are around 17 per kilo. And why is it so high? It's not just the cost of electricity, it's also the cost of capital, because wind doesn't, if you have to set up an electrolysis system, all that, a very large one, it's expensive, But if you're going to be using it only 30% of the time, it is like a sitting idle. The asset isn't producing anything for you. So that's part of the problem. You can't run an industrial process on something that when the electrical supply is intermittent. And that really is a big penalty. Of course, if you produce the hydrogen in one place and you're going to use it somewhere else, you have to look at also the transportation and storage. I should have mentioned in my previous slide itself that you're going to be looking at three different aspects. It's the production aspect, then the storage and transportation options, and then the consumption options. We touched on the consumption options a little bit earlier. We'll touch some more. Okay. So we have various different forms. You can use it in terms of compressed hydrogen, or you can liquefy it or convert it into a chemical like ammonia, methanol. These are atmospheric pressure. They don't have any, you can store them under normal conditions. And then you could ship them either by pipelines, some cases. Hydrogen has got a very, being one of the smallest molecules, you can really get through the tiniest pores, and it also embrittles pipes and causes leaks. And it's a nasty thing in that regard. And you have to be careful about it. So that's one of the reasons they don't want to increase when shipping hydrogen with natural gas pipelines more than 30%. Then you have the normal trucking or shipping things, or if there are some other technology that I haven't thought of. And physical storage, often they're even thinking of doing it in caverns, salt caverns in particular, salt mines. There's another way of storing some hydrogen, but it does leak. It has a very high leakage rate, and so it's better not to do it that way. But steel tanks work fine. Let's look at it. So we can use it for power generation, as I said, but we use a lot of 50 megawatt hours you use to just produce to electrolyze the hydrogen. And then if you're going to produce the hydrogen, it seems to be going in circles. There are some good heating applications because you can get very high temperatures, and certain industrial processes require high temperatures, which hydrogen would be important for. Metals refining is an area which you cannot do any other way, or either electrolysis, which is how aluminum is produced mostly, or you can use dry refining, which is with hydrogen. It's used a lot in fertilizers, and a very large amount of it is used just in the petroleum industry itself, where they take part of the petroleum, produce the hydrogen, and then use it to upgrade the oils to get where you become the fuels that we use in our transportations.
So I have a quick question for you, Raipu.
Yes.
How toxic is hydrogen compared to other materials? The gas
Hydrogen
is going to make you sick with cancer.
Hydrogen is as a toxic. It's not toxic. Hydrogen is not a toxic gas as far as I know. But I mean, it's only because it displaces something else is what the problem is. I don't think it has any toxicity as a biology, in that way. It doesn't bind with it doesn't take with our, like CO or CO2 would. CO2, of course, is not that toxic unless the concentration is very high. That happens when they remove the oxygen from us. This doesn't do that. I don't think it has much of a toxicity. I could be correct, I could be wrong, but that's my understanding.
Yeah, that'd be a good thing.
So here's a comparison of a battery electric vehicle versus a fuel cell electric vehicle. So we go through some steps. So if you have an e-car, the battery electric vehicle, and let's say you have a power generation that you're starting with 100% of the power, you're giving it, you get to the through transportation and storage, and kind of by the time you get to the car, you're down to about 80, 90%. But then you've got to put it in the battery and then you take it out. There's some cycle efficiency of, there's a loss of that. Some power is lost in charging and discharging the battery. So ultimately you get between 70, well, this is pretty low, about 90% efficient this is the overall efficiency. The overall efficiency is between 70 and 90% when you go this route. Let's look at the route because it's storable hydrogen. Electricity was the problem, was always, do I need a battery? And batteries are not the best ways to store. You cannot store very large amounts of electricity with that. So hydrogen was the option. And so let's see if we compare it with a car situation. You start with 100% of power grid hydrogen, power grid electricity. You go to the electrolysis, you're down to about 70, 75%. You got to compress and liquefy, you drop some more. You go to the transport, your filling station. And the fuel cell, again, has an efficiency of about, about 55 to 65%. So the total efficiency of the 100 is only about 25 to 35%. So it's like, yeah, if you want to save thing for a rainy day, in this case, when the sun won't shine, if you want to do that, it's okay. But it's like going to a bank to save your money, and the bank charges, first of all, 30% to deposit it, and then another 30% when you're taking it out. So that's why it just drops so much. You have to be really hard pressed to use such a banking system.
So Ripu, sorry, this
Yeah.
is Booker interrupting. Does that mean Toyota's emphasis on the Mirai, and I guess it's also Honda?
Yep.
Is that just plain mistake on their part? I mean,
I don't understand why they do that. You are right. If you got that sense from me, that's my opinion. That's my opinion. I think that is when Mirai started, batteries were not very efficient either.
Okay.
And the range of battery was pathetic. So that was the reason Toyota did not go with the battery developments. It went into hybrids, and it wanted to make mildly hybrid cars, Prius in particular, in which their hybridization was for only a little bit, but the big efficiency savings that you get in your Prius, and those are wonderful cars to drive, having driven them for many years myself, it's because they have lightened the car. It's a small engine, but that engine is run at almost its optimal time, efficiency levels. And so that's how that works. But and so Toyota's thing way back in the early 90s, when I was talking to, when I was in conversations with them, that was my understanding, that why they didn't think, and the batteries at that time were pretty expensive and also did not have much range, and they were very heavy. So the lithium-ion battery technology has really made a big difference. And so today, if I were to be starting, I would not be looking at a hydrogen car, but I know there are some car companies are still looking at making fuel cell vehicles. But these numbers are hard to beat. This is what it comes down to. You lose your efficiency completely. I don't know that they will make any sense. And if I have if I had a lot of surplus hydrogen, I'm sorry, I misspoke. If I had a lot of surplus clean energy, maybe it may be worth saving it as hydrogen. But we have a shortage of clean energy. We don't have that luxury at the moment.
And Ripu,
So-
how does that compare to just a gasoline engine straight, the overall efficiency? Isn't that in the 25-35% range?
So we are talking now that the difference is that, so in gasoline, all the energy loss is happening over here. So if you want to look at it in an electric car, you get about, I've looked at it in terms of 4 miles per kilowatt hour. And if I look at the the gasoline car, it's about the same. But first, I mean, in terms of after converting the megajoules, it's all back to the same. They are very comparable. But of course, in one case, you are emitting tons of CO2. In the other case, you are not.
Right.
Or the CO2 are being emitted at the time of the electricity production. So an electric car is not a zero emissions vehicle, it's a remotely zero emissions. And those remote zero emissions depend on how the electricity was produced.
Got it. Thank you so much.
Question, why can't we just burn the hydrogen to get the, like we do the gasoline to propel the car?
So that's called the ICE engine, internal combustion engines with hydrogen, H-ICE. We don't have very good H-ICE engines. I don't know, that has been hard to build. So they can blend some hydrogen, even in turbines, they don't do it directly. I think there are concerns about it. It's a possibility. There are hydrogen ICE engines, and that would be fine. But then you do lose in your electrolysis. I mean, it's about 50% loss right there. They're not showing us 50% loss over here, but they're showing a very good electrolysis machine. I think the commercial ones are generally about 50% efficient, and 75 is the other one. This is the new ones that are coming up, alkali with the solid oxide membranes. They have those, but they're not as yet very large. Now, electrolysis and fuel cells are often, you will hear that, well, we don't have the thermal efficiency losses that heat engines have to go through, and because this is electrolysis, this is where the electrical energy and the chemical energy is through the Nernst equation, we get very high efficiency. That is just theoretically, yes, it's possible. But as soon as you start drawing current, the resistance inside the cell, the overpotential of the batteries, that's the way that in the fuel cell or in the electrolysis, that's where the losses are. It's not in the open cell potential as we talk about. I don't know if that's, that's like what is the potential of the electrodes when they are dipped into this electrolyte, and will they drive the reaction or not? That's at equilibrium at this when you are not putting any load on it. As soon as you put some load on it, those bets are off. And that's where your efficiencies begin to fall. So open cell means no draw, no load. Yes, you have very high efficiencies. You can have, theoretically, they are very high, very good. Fuel cells are excellent. So are electrolyzers. But in practice, they are not. And you don't want to be doing this at a very, very slow rate. You want to do it at a reasonable rate. That means you'll be driving the current through it at so many amps, so many coulombs per second or something like that. You want that. You don't want it to be waiting for eternity to charge. As such, it takes longer to charge the batteries.
So Ripu, may I add a question? I'm also a Prius lover, My current Prius is a plug-in hybrid, which
Oh,
means
wonderful.
I run it on electricity as much as I can, and then when necessary, switch to gas. So why would Toyota not make the Mirai with a high-capacity battery instead of a low-capacity electric battery? Something you could charge and then only draw on the hydrogen when you really need it.
Well, good question for Toyota. I don't know. I really don't understand that. But I know that when it started, that was the way, but I don't know what the drive is right now. Why are they pushing all hydrogen cars and the hydrogen? Well, you know, for when you want larger capacity and larger ranges, you can swap the big advantage because it is a storable. You can swap the tank very quickly, or you can fill it very quickly with this as opposed to a battery.
Well, one possibility, you're talking about Japan, that doesn't, they have nuclear energy there, but they don't have any fossil fuels. So for them to generate hydrogen, from an energy independence point of view, might be practical, more practical than other places,
Right, right. They import pretty much all their fossils. Their coal mines are in Australia and Indonesia. And oil comes from also global supply chains, not local. Anyhow, I think let's move on to the next. If it's okay, are there any other questions for this one? We can pause before I move on to the next part.
Well, I'll tell you, 5 or 10 years ago, sometime in that range, I attended a lecture by the head of Toyota America. And he said that they were working on hydrogen and that they had modified a Toyota Highlander, which is an SUV. I have one.
Yeah,
And, to operate on hydrogen. And their major concern apparently was that the hydrogen would be unsafe. So they actually fired bullets into the hydrogen tank to see if it would explode, and it didn't. But he didn't tell me if he went to a battery or if he combusted the hydrogen. What they did say is that the residual is water.
Yes.
Which at least I implied to me that they were burning it. So
well, it also has that same thing in the fuel cell when it produces electricity in the fuel cell. The hydrogen combines with air oxygen to produce water, and electricity is the result. So it's just the opposite of electrolysis is what happens in the fuel cell. It's the same reaction, H2 plus O2. In the one case, starting with water and driving it up the hill to make H2 and O2. In the other case, you are combining H2 and O2 and going downhill to water on the electrodes. And then there's your current that comes out and that drives. So it's the same reaction. One's going forward and one's going backwards. Oops. Okay, so let's turn to carbon capture and sequestrations. Is this my next slide? Just a minute. There it is. Wanted to show you, take a second to, just wanted to get that something off, but as soon as I touch the trackpad, slide changes. This slide basically shows the global CO2 flows that are there, so we are doing about 50 gigatons of, or sorry, 30 gig, yeah, 35 gigatons of CO2 are being added every year from the energy use. And this one's showing all the different things. So like here it is, 13 gigatons from energy, 3 gigatons from building, 7 gigatons from CO2. In the atmosphere itself, total, there are about 3,000 gigatons. But then there's a fair amount thing that happens from agriculture, land use change, and then there are sinks also. So there are fairly big vectors here. So, you know, so it's, but the net is about 35 gigatons of carbon are being added to the air each year. The reason for carbon capture is that we already have so much in this 410 ppm, 420 ppm right now is substantially more than, and it was going to cause a fair amount of warming and all the subsequent things, which means melting of the ice, this rise of the sea levels, and many other things that will follow from that. So we have to somehow draw down. And carbon capture says, so there are simply why we are looking at it is, we don't have clean technologies enough, but energy is needed. We need lots of energy, and more energy sources are the fossil. Well, can we extend the use of the current ones by using carbon capture? It's a choice that is being made, but it's difficult. We don't want to, but maybe sometimes you go with what the less of the two evils. And then the places which are difficult to electrify or decarbonize, for those cases, CCS, carbon capture and sequestration, may be okay. And bringing it, the already emitted ones, even after we have stopped emitting anymore, we may still have to do something to draw it down. And so the idea is that you go to the source of the carbon emissions, where it is the CO2 is coming out, you capture it in some facility, you transport it to some location where you could then either inject it into deep saline aquifers or some oil beds that have been used up, so use it for enhanced oil recovery, or you could use it, you know, in some minerals so that you can, or you can contain it in a, convert it into some minerals. We'll talk about that in a minute. There are some basalts and things that can be used for that purpose. So basically, you would have taken the CO2 that would have either been released to the air, or you could capture it directly from the air from somewhere, and then take it out of the atmosphere and bury it somewhere. When combined with the biomass burning, actually carbon capture and sequestration would be a net negative emissions energy source. That's the other, at least you will hear about it in BECCS, they often talk about that. You'll see newspaper reports about it. I think biomass energy is, if it is already there, like in a landfill waste or something like that, or municipal waste that's there, mostly biomass, that's one thing. But if I'm going to be growing forests to chop them down, to burn in a thing, and then capture the CO2 from that, it seems like a really Rube Goldberg in kind of a contraption that's doing nothing ultimately, but barely. And it's only through creative accounting that such bioenergy could be considered carbon neutral. Because most often what happens is we cut down forests. The very first year we emit a lot more CO2, and then it takes decades for that carbon to be absorbed by the, but in the accounting, they consider biomass to be carbon neutral because on the long run, it is not. That is true. In the long run, it is not, but in the short run, it's terrible. And and we have a short run problem here. We don't have lots of decades for the carbon dioxide that we emit from cutting down trees to be reabsorbed. And but why is this accounting considering the biomass considered zero emissions is something I don't fully comprehend.
Well, before you skip on to the next slide,
Yes.
can you go back? I just want to make the point that 40 years ago, or more than 40 years ago, when I was working on this problem, the idea of sequestration in the ocean was popular. That is, if you pump CO2 to a sufficient depth, it liquefies and it's denser than water and it just runs downhill. And
Yes.
you end up with great large pools of CO2 in
Yes.
deep ocean areas. So the idea was to find coastal areas that have a dramatic drop off in the depth and build your capture plant right there at the coast and pump it. And you never see it again.
It didn't work out that way, did it?
No.
It had lots of burps.
I had a question as well. How much energy
Seismic activity and all that, and then those lakes, the CO2 density is very close to that of water. And seawater further down is denser. And so it isn't, and it mixes. It doesn't necessarily stay there, and there is no guarantee that it's going to stay there. It leaks out. So this was not a very stable. That's why the ocean, that sequestration in the deep ones, in the ocean depths, has not been pursued a whole lot because when they tried to do some measurements, I think they were finding a fair amount of leakage and mixing.
How energy intensive is it to capture it?
Pardon me?
How much energy is used in order to capture it and
A lot.
pump it
a lot.
into a lot?
It depends on what the source. So here we're going to think that the next slide will talks about first of all how this has gone on. If you look at from 92, actually, the first Earth Summit was in the 70s in Rio, but then they were really concerned about CO2 emissions beginning to rise, and they were thinking that 350 would be pretty bad at that time. And 20 years later, again back in Rio, they saw it actually was beyond 350, it was 360. Emissions at that time were about 22 gigatons per year. By the time we got to Kyoto, then the pronouncement stated goal was, okay, let's reduce it, try to bring it back to 350 by 2022.
Let me just canvass the group here. How many slides do you have? Would this be good to do another time, or should we just keep going? Let the group decide. The carbon capture will this be like another half hour, you think?
I don't think so.
Okay. All right.
This is a shorter part.
Okay,
Hydrogen
good.
was a bigger part.
Yeah, I mean, it's really interesting. I don't want to shortchange it because I actually have some investment in this technology.
So there are some interesting questions that come up. With the point that I'm making in this slide, maybe we shouldn't dwell too much on this one, is a pronouncements aside, the reality is that atmospheric CO2 concentrations have been going up, 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 in line with what I saw, what I showed in the beginning, that our consumption of energy for the fossil fuels has been going up, 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 and there is no abating it. And that's not because we like to do that. It's because we like to live. And we have to, we need energy to, that's our sustenance. So I just want to show you all the difference. Of course, I'm not going to talk details in the technology on this, but just laying out over here all the different options that we have. In terms of capture, we can look at stationary sources. Those would be like power plants or industries. And in like smelting in the iron industry, you get very high concentration of CO2 coming out of the blast furnace. Power plants, those things produce about 12% CO2 in the flue gas that's coming out. So higher concentration it's good. So maybe you could capture it more easily. Capturing it from air, means you'll have to, it's 400 ppm, so you have to move a lot more air to capture it, to collect it. And when things are, there's a balancing act here that's required. So these are the stationary sources: power plants, industries. Then we have mobile sources: the cars, trucks, ships, airplanes. People are even talking about now putting something at the end of the car tailpipe. We try to put anything to block the exhaust, you lose efficiency of your car also. So yes, so in power plants, if you put something as a capture system, it will take some, it'll cost you some energy. And that energy penalty that you pay is on the order of 13 to 15%. That's from the power plants, from coal-fired power plants, which have the highest concentration of CO2. I had a project where we looked at the power for capturing from a natural gas power plant, and the penalty was much, much more severe. Maybe there are better stuff that's available now that they have, but it's not just the dilution of it, it's also at what rate you need to do. There are lots of engineering considerations that come up. So it's not a simple thing as just because it's dilute, it's enough. That it is going to be more expensive just because it's more dilute. Natural gas has got less CO2 per megawatt hour of the concentration, but that's one of the factors. It turns out that even capturing from air, the thermodynamic energy penalty is not that much more. The big energy consumption is in moving large quantities of air over your whatever device you're using to capture it. Then you have to compress the gas or somehow pipeline it. And what do? Now, in terms of use, as I said, the only one that's using any significant amount is oil wells, because now you get a valuable product out at the other end, more oil coming out, which means when that burns, you could produce even more CO2. That really doesn't solve the problem. People are talking about, well, we'll make fuels out of it. Making fuels from CO2, we saw what that was like with hydrogen also. You can't start with water and make fuel out of it, because you would put in more energy ultimately than you will ever get out. And the situation gets even worse when you start with CO2. But that doesn't stop people from pronouncing it. There are lots of projects that are going on, and there have been quite a few of them, time and time again. And I really have to shake my head at that. I said, what's the point? Yes, it's a green fuel. It's a green fuel, correct, if you have captured all of it, but it's not an energy, you have really made it so much more difficult. If the object is only, they say you cannot fly planes on any other thing other than a jet fuel. So I'll make jet fuel like this. My recommendation would be, just don't go into making fuel, just capture the CO2 and sequester it. That may be the easier way to compensate for it than trying to put more energy and convert CO2 into a gasoline or a jet fuel and try to fly planes on that. So dispose the CO2 in deep ocean trenches. There was the potential disastrous release of CO2 from seismic activity and other instability. That's what killed that part. Enhanced oil recovery, converting CO2 into fuels. And then the last one is storing the CO2 in silicate deposits, the olivines, the basaltic rocks. So what we need for these is some kind of a base. CO2 is like an acid, and we need some kind of a base. So either an ammonia or so there are kind of reactions, or an amine, or lime. But lime doesn't exist on the Earth's crust. It's always the carbonate already. So you have to put in a lot of energy to break the carbonate and you get CO2 out of it. The only basic oxide that we have available plentifully on the surface, or in the, not open, but maybe slightly deeper, is, or in the crust at least, are these olivine or silicate or basalt deposits. The simple formula for that is like a magnesium silicate. So the chemical reaction, if I write simply, is CO2 plus magnesium silicate, making magnesium carbonate and silica. So I have a gas and a solid going to two solids. And this is happening naturally. It's happening in many places. Oops, I see I missed my subscripting of the 2 over there. This is actually has happened on Earth. There are many of these places in basalt rocks. If you look at the functions, I remember I was walking across the Kilauea volcanic bed, what do they call those? In Hawaii, you could see, huh?
Lava?
No, the lava beds, but the mouth, it's a dead volcano. That part is the dead one, where you get to walk across the basalt, and you see some crevices and all that, but you can see how the silica has been formed over there, and the white of the magnesium carbonate and all that. You can see that reaction over there. It's happening. And estimates are in Iceland, there are many places where it's happening very rapidly.
Well, just to throw a little ice water on your reaction, if you're going to get a gas reacting with a solid, you got to grind the hell out of the solid in order to get.
Absolutely, that's the problem. So there are 2 different ways of doing it. One is you take the salt rock out and you grind the heck out of it, or else it self-seals. Or you can take the CO2 to a location where geology provides you with the right kind of temperatures, and steam, the hydrothermal conditions for it to occur. So it doesn't happen so easily. But there are places. And again, Iceland is one of them.
So your suggestion is that you would what? Capture the. I hate to pick on you. I love you, but my God, you're suggesting we burn oil in Texas, grab the CO2, transport it to Iceland and react
No,
it.
we don't have to go to Iceland necessarily. That's just one location where I can see it, but there are many places here in Oregon. There are lots of places. The whole Eastern Oregon has got a lot of basalt over there.
Finally, something useful in Oregon.
There are places.
Watch
And
it.
it's a matter of, but it's hard. It's not easy. There's no doubt about it. It's expensive.
Yeah, but you know,
And
you're trying to
capture-
save the world. So, I mean, it's kind of,
Yeah,
these questions have to be asked.
these have to be asked. They have to be asked. And you're absolutely right. And it's not going to be easy. And here's the thing. So flue gas, you know, if I have on the one hand, here's a cartoon of showing how the capture is done. So let's see if I can follow this. Flue gas comes in and you come out with some contacting liquid or solid or something, which is the contact tower. And what happens is there's the CO2 enriched one is going out from the bottom, and other gases flow out. And then this one is then put into a tower. It's a stripping tower, which is a little higher temperature. So I think this was taken from the select salt process. This is a liquid one, where the flows are, the way it's shown, but you can do it with, you know, the concept can be seen. At one temperature, at the lower temperature, you contact the thing, you get the CO2 rich solvent, and you put it in the stripping tower where you put energy and steam, and then you strip the CO2, and the CO2 comes out as a strong, because all the other gases have been removed over here. CO2 was caught over here, but the nitrogen and water, that went up over there. So you get this, then there's lean, after the CO2 has been removed, that solvent can be recycled. It goes through back and forth. But if the concentration of the flue gas or whatever's coming as CO2 in that is very low, I need a very powerful absorbent. If I have a very powerful absorbent, then I have to put more energy here to release it. So it becomes a balancing act. And to minimize this wasted heat, did the thermodynamic analysis, this heat of absorption has to be somewhat moderate. It's not very high. And so lime is very strong. You know, you can't leave lime outside. It'll absorb the CO2 from the air right away, but we don't have lime. But here it is in Iceland. This is the Climeworks plant. They are doing direct air capture. Address was, it doesn't matter which source emitted it. It's from any mix, you know, fixed or mobile. Doesn't matter. You don't have to capture it here and transport it. You can just do it over there. And what they're doing it is they are converting it into the basalts that they have over there, right there, without grinding. They just pump it down. It's slow process, takes a little while, a few years, but in a few years, that CO2, that rock is now totally, the CO2 has been mineralized. Let's see how it works. Right now it's fairly small scale. Thinking of making larger scales, but you know, 4,000, 10,000 tons. We are talking about billion tons. There's a factor of million in between somewhere. So, and all these things work best if you have a kind of a waste heat source available, which they have. They have lots of geothermal. And that's why it's working over there to some extent. Anyhow, the current status, there are about 30 commercial facilities in operation, with a combined capacity of 40 million metric tons. as I said, most of these are for enhanced oil recovery. Additional 160 projects in the development, et cetera. They have a target of 5 billion tons by 2050. I don't know what's going to happen, but whether they get there or not. Currently, most facilities for capture are in industrial sources where you have very concentrated streams of CO2, like steel, cement, hydrogen plants, ethanol manufacturing, breweries, things like that. Breweries for both for biofuel productions and all that. They have a very concentrated CO2 stream. And there are direct air capture. There are about 15 projects with a combined 9,000 metric tons a year. And I showed you the one in Iceland sequesters the CO2 into the salt. Okay. Well, what do you do with it? That's why you talk about CCUS also. I say, well, let's make carbonated drinks, but that doesn't help with the climate. And the scale, it's a mismatch. It's the mismatch of how much CO2 we have to remove, and that we just don't use anything in that quantity. That's the big problem. One other place that we had that has been talked about, and I'll just leave you with that, is to grow microalgae and to harvest the solar energy for the algae to grow, and then use the algae to extract biofuels from that. That's a possibility. I've got several projects that I did that on that myself. It's still early, and when I retired, the latest, most promising technology was with using synthetic biology, and they had genetically modified or looking at strains of algae that can grow very fast. But the other inputs that you needed were a problem. They need nitrogen, they need fertilizers also. And so the question was, can we use some consortium of other bugs that can fix nitrogen from the air directly? It's an active research still going on. Well, this is the same thing previously I talked about. So this is I found that picture. This is how I was going to show you the slide as to how much the power losses, but I showed you the Volkswagen and made that drawing. That looks pretty. So I'm going to stop my talk here. Let's have some general discussions going on. What time is it? Oh gosh, it's already 10:08. Okay.
Ripu, it's been a tremendous and normal tour de force by you of covering all the aspects. And I just love that. It isn't just pushing one thing, it's showing the consequences. That's what you did in a cubic mile of oil, and it's just wonderful. To switch a little bit, methane clathrates.
Yes.
Any hope for those? I mean, that doesn't help, but it's a source of methane.
Methane clathrates are the things that we are afraid of, that I want to stop sharing so I can see everybody. Where is my stop sharing?
Your options here.
I'm not seeing my stop sharing.
You should be able to do that.
Stop share. There it is. There it is.
Okay.
Thanks.
Yeah.
Yeah. As things are getting worse, with the climate, there are so many methane clathrates that are under in the polar region, in this Arctic as well as Siberia, and we're just afraid that once that comes out, and the methane is in short term is about 80 times more potent than CO2. So when they talk about, yes, I would like to see us use more natural gas because it is cleaner than coal in many cases. but we have to absolutely ensure that the CO2 or the methane leakage is not there. We really have to, anything more than 4% methane leakage, and we are not, because of the big disparity between the global warming potential of methane and CO2, anything more than 4% of methane wipes away any benefit.
You know, one technology that does make a lot of sense is heat pumps. I was
Absolutely.
I was just looking at, you know, if you burn natural gas and use it to run a heat pump, you know, use the electricity from it to run a heat pump, you're using about 30% as much energy as if you just use resistive heating from electricity. The electricity that you need to run a heat pump is about 1/3 what you need to heat your house compared to resistive heating. You know, it's
Right.
almost like getting something for nothing. It's
Yeah,
a miracle.
you are pushing, you're not creating heat, you are moving the heat.
Right. But
So
you're not
you have,
generating any
you
you're
have
generating.
you have a 2-to-1 benefit over there. But you know, if I burn 3,000 BTU of methane, I get 3,000 BTU of heat.
Right. But
But
you could use the methane to run heat pumps, you know, and
well,
it'd
but
be even
then-
better. Yeah.
that to heat the place, or to heat the pump, then the efficiency drops. Then if I'm using methane to make electricity, I could drive the heat pump with electricity. Then
Right.
I lose my I have 30% efficiency over there of
Well, you could
methane.
use the heat pump. You could use the methane directly to run an engine that would run your heat pump. You know.
Well, if it's a heat engine, I've lost my 30%. I'm back to 30% efficiency.
Yeah. Yeah. All right. So you kind of you wind up with one. You wind up just one. The same. Yeah.
Same. So that's right. So that's why in this equation, when we convert the different fuels, you look at the input fuel. So if you give me electricity, 1 kilowatt hour of electricity is 3,400 BTUs. But in practice, actually, if I have 1 kilowatt hour of electricity, I need to burn 10,000 BTUs to get that. So that's why you got to make sure when you are mixing fuels and all of them in those charts. That's one of the reasons my cubic mile oil book, I'm noting I'm going to redo that. It was forever taken a long time. So I just go with what people are producing or reporting. And BP has done a good job. BP has been keeping track of the efficiency factors very rigorously. The only thing they have not done is use or provide any source of the non-commercial fuels, which is biomass. And there is so much of biomass that is used worldwide. About 3/10 of a cubic mile was way back when, and it doesn't show up in their charts. Scott, you have a question?
I had a question on,
first.
oh, good.
Go ahead, Tim. What do you want?
I had a question. In a typical power plant where they use lime in the scrubber systems, either as a dry lime or a wet lime, and then it goes typically to a bag house where it's pulled back out. But in my practice or understanding, typically that limestone then goes to a landfill. It's not had to pull back out. Is there any possibility that then that limestone could be used like in agriculture or something? Because right now, what happens in the typical power plant, it just basically ends up in a landfill.
So they don't use a whole lot of lime. I mean, they don't try to capture all the CO2.
In a typical scrubber, they inject limestone into the mix, either as a dry limestone or as a wet. And then in the dry system, the gas then goes to what's called a bag house, where it's basically like a fancy vacuum cleaner, where then it's collected and then they shake the bags and dump it into basically a dumpster
Okay.
that they fill up with the limestone that's absorbed the CO2.
That's
No,
mostly for
it's not for
sulfur.
CO2. It's
It's
not for
sulfur.
CO2, it's for sulfur. It's for other acid gases like sulfur, and for this, they don't capture CO2 to any extent, any significant. It's
Because in
only
your slide, you
sulfur-
had them capturing the
Sulfur and nitrogen
CO2.
oxides. Sulfur and nitrogen oxides are the ones that are, those
Okay.
acid gases are caught. But CO2 is a weak acid, it doesn't. And it's limestone, which means it's already carbonate.
Right, it's powdered, but yes, yeah.
It's not lime, it's because, yeah. So, yes, and that deposit is, it could be used for something, but mostly people don't like to, there are not too many uses. One use that that is there is for wall boards. It's used in making gypsum boards. But if there is a fair amount of carbon residue in there, it gets a different off color and it has no market value.
You know, the thing that bothers me is it seems like, you know, we have probably one of the world's great experts here in energy, right? It's kind of you have a good idea. It looks like we're kind of screwed. That's kind of what I get out of all this. We haven't really come up with a solution. I mean, we talk about fusion, but it's, you know,
Decades,
50
yeah.
years out. But
Yeah.
that probably would actually be, if it could be done, would be the holy grail.
I know that is fusion. I knew this with the news about fusion this week that somebody may ask me. I have my own thoughts about it. I'll spare that for now. There are two hands that are up, so let's listen to those, and then maybe I'll share you.
I think Dave was first.
Okay. Two things. One is I went to a lecture a couple of years ago. A local company on Long Island is working on an aerodynamics process to get the carbon dioxide out of the exhaust stacks from power plants or factories. I haven't updated that, and I'm not sure how successful it's going to be, but one of the problems with it was it took about 20% of the energy from the generating plant to run this capture process. So
Right.
that was a big
Yeah.
disadvantage to it. It took so much energy. The other thing I wanted to mention
So
was,
for that, you know, if you can allow it to, so that's just a cost. So you've got 80% of carbon-free energy. That's not bad.
Yeah.
that's what they're hoping.
That's not bad, actually. And,
Yeah.
you know, if you look at as they're talking about $100 per ton of CO2 is the price they want to price that. The capturing cost by most of the air capture or some of these, they are really running into many hundreds of dollars per ton at the moment.
But then they
So
have the added
from a
problem.
power plant, if you can do it for $100, and $100 fee translates to about 8 cents per kilowatt hour for a coal-fired power plant, 4 cents a kilowatt hour on a natural gas-fired power plant. That's the price. Or on a gasoline, it's equivalent to about 80 cents per gallon. That's what $100 per ton of CO2 will,
And power costs like 10 cents a kilowatt hour now. What do we pay for roughly? Is that
depends where. I mean, in
Yeah,
California,
roughly.
we're paying 35 cents.
35 cents? Okay. So,
No,
you know,
here we are paying only 13 cents.
okay. But 8 cents, I think, I don't know, to save the planet,
Yeah, but you have to
No, but
convince
that's
the power
8
company.
cents if you're producing it from coal. That's why the cost over here is going to be less in
Yeah.
So the coal, the worst would be that. That's what it's not a lot. It's, if you can do it for 8 cents, I mean $100 a ton, it's okay. It to save the world, yeah.
Yeah, but you have to convince the power companies that
I
they
think
should.
our company is not the one that's going to be the problem.
Who's the problem? The politicians?
Yeah.
I think there's more. I mean, even the public. I mean,
Yeah.
and it can be made into a thing.
Right.
We see that all the time.
Right.
The other point that I wanted to make is there's a lot of work going on right now with electric airplanes, but they're all for short range.
Yeah.
I'm not aware that there's anything going on to replace a 747 or a 777. But if they get it to work with batteries short range, then who knows, 50 years from now, what that's doing. And the other problem is trying to capture the carbon dioxide out of the jet exhaust on an airplane. That sounds like a pretty difficult.
Exactly. So why not? That's where the direct air capture comes in. And I say use direct air capture. The penalty for just having the dilution factor is not that severe. And we could probably do it for about, if not 100, maybe $300 a ton. And I don't have to do, a whole lot more. It doesn't matter where the plane is flying. It doesn't matter where it is. I find a source. I mean, I can build the plant. And the capacity is so much more. Just on one island off the Iceland speck over there, you can estimate the amount of CO2 that is locked in the rocks over there is 6 times the entire inventory of CO2 in the atmosphere. So it's that once you cut from gas to solid, there's just so much more potential over there to save it. So that's a possibility. But all these require lots and lots of copious amounts of clean energy. They're not a source of energy they need. So I need to make more and more clean energy, and I don't know where else to come from. When there comes the hoopla of the fusion, my fear is that people are going to use this to stall the development of newer modular or smaller nuclear reactors, or any deployment of any nuclear reactors, because that's one technology that we have already in the bag. And we could.
You have to make
This
it
will be-
profitable. You have to make it profitable for corporations
You have to.
somehow through, sometimes you do it through, government
Yes.
incentives and that sort of thing.
Yeah. Right.
Yes, we have to make it profitable. I mean, our electricity market is so, I think Booker was involved perhaps in that project when California went through the deregulation. I mean, it has been the biggest disaster in terms of how unstable, how the reliability of the power sector has, all the places which now participate in this regional transmission organizations, RTOs, that has really hurt. It's made it very difficult to make any investments. The revenue streams over there are, and the price, they make no sense. They make sense in some way. They do, but if you look at this systemically, you look at it from a national perspective, but they have just broken it up, and nobody has the responsibility for reliability.
Yep. Yeah.
That's
Scott?
my question then. So hydrogen electrolysis, I appreciate your point on the capital costs, and maybe you only use it 30% of the time. So I guess it's maybe only feasible if you've got free energy, and maybe not even then. I guess I had this notion that they've got all these windmills and solar in LA, and they just can't get rid of the power. Is that realistic? Do you think there's a future where we'll just have money or energy? We just can't, we'd have to throw it someplace, and this could be viable, or is that a pipe dream?
No, that's true. That's one of the reasons that they were talking about it. If we put in so many windmills and so many solar panels that we cannot use it, then let's make hydrogen, or let's make water. Let's desalinate water and all that.
Right.
But
Do you
that's
think we'll get to that? Will we
don't
have so much energy? I mean, it's not much now. Like you said today, we're making, I don't know, is the cost of the the electrolysis plants that's stopping them now? Or is it that they don't have enough excess electricity to make it
we
viable?
don't have excess electricity.
They don't, right, okay.
Don't we sometimes have excess electricity?
For brief periods. For
in our-
brief periods.
I mean, even the Columbia River, do they use every bit of that?
Well, they can store that at least, right?
Yeah, but you could take
That's
this, if you needed to store it, you would store it
no.
in hydrogen, maybe,
Yeah.
create
We don't-
hydrogen.
There's not a lot of, you don't see us having,
We don't have enough clean energy.
yeah, okay. And you don't see that changing with, yeah, okay, all right.
I don't see that. You saw how a tiny sliver that was.
Yeah, right.
Yeah, that's
a good
sad
point.
every time I see that.
Good point, yeah.
Well, desalination right now in Israel is going to produce about 90% of the nation's water needs.
Yeah.
I don't know what their energy source is for.
Nuclear. Nuclear.
Oh, really?
Yep.
Okay. Thank you.
Good to know.
It makes a lot more sense. I mean, if you could, at San Onofre, we closed it, but we could, if we have those desal plants that we're not using either in California.
Do you think there's a change in nuclear? I read Bill Gates' books, and I am, in the last 2 or 3 years, I've seen such a resurgence. I would have written it off 5 years ago. Do you think it has a chance?
I do.
Okay.
I am seeing a real change in the last 2 years or so, 2 or 3 years. I have noticed that in my talks when I give, I don't get the usual questions that I used to get. I would always be bombarded with, oh, what about all the radioactive waste? What about this? And what about that? What about Chernobyl? What about Fukushima? Now I get the questions, well, how do I scale it up? How do we get people to accept it?
Right.
So there's been a shift.
Good.
So
Well, is there a good reason for that? I mean, are the nuclear power plants going to be more safe?
The power plants have the best safety record. Deaths per kilowatt hour or terawatt hour, or however you want to define it, is the fewest than anything. Better than solar, better than wind.
Speaking out of that, I was looking at a book today in the library called Super Fuel, and it was extolling the advantages of thorium reactors.
Thorium.
Is that for real?
Thorium is for real. We had, Thor Kahn's person, he didn't join, but he did. I did a few weeks ago, a few months ago, sorry. We had Bob Hargraves give a talk here on thorium and small modular reactors. And so, he got your announcement about this talk. And so he wrote to me, he says, Ripu, why don't you talk about capturing CO2 from the seawater? Seawater has even more CO2 than this. And yes, that is true. I had a project that I worked on for a while of the concept. I just did the analysis. I didn't do any real lab work in it. That was that if we take you consider an aircraft carrier, the situation is okay. So they have to produce a lot of jet fuel. So they have a lot of ships that have to come to provide with jet fuel. Why can't the aircraft carrier with its nuclear power that's there extract CO2 out of the seawater, which is fine, and then convert the CO2 into jet fuel? And the calculations showed that if we did that when the power plant was dedicated to just making fuel and nothing else on the ship's operations, you could make enough for one sortie.
Oh. Okay, all right.
So the advantage is, we will eliminate all the boats that are supplying the fuel, which are more vulnerable. That didn't apply. So yeah, it can be done. But
Well,
there's
you know
still a
what?
lot of penalty in terms of moving the seawater.
So Raipu, I'm thinking I'm gonna stop the recording now. What do you think? Are we
Yes.
about
I
there?
think we could talk all night, but we should stop.
Yeah, I
soon.
think we could, but I'm not,
We can
I've never
talk.
recorded an hour and 45 minutes.
wow.
Hopefully it will work.